So, as said, welcome. So my name is Gerd Duscher, and I want to introduce you to all the relevant, or hopefully I make a good decision to introduce you to all the relevant terms in electron microscopy that we are going to need. Let's go back here a little bit. This is the wrong one. I'm not. This is a notebook, so I will do that with Jupyter Notebooks. If you want to find them, I put it in the chat. It's over here. That's not where it is. It's in Gerd Duscher on GitHub, MLSTEM 2026, day 1, and it's at 9 a.m. If you click on that, then you also can open it in Colab, and you can follow it. The trick in Colab is that if you run that, so it's just some housekeeping that we're doing right now, it will install everything we need. And after that, we will have to restart the runtime, restart the session here. The reason is we are using interactive plotting of Matplotlib. So if you do that, we'll have the animations and everything is ready to be used. So we don't wait for that. I put it on my computer. In Python, after you have the environment variable set, which I already did, then we load it. So I'm not sure how familiar you are. So some people are very familiar with the microscopes. Others are familiar with data analysis. So we have all of them here. So we check that. So it's loaded. Now we can get into electron microscopy. In this graph, we see we have an electron. We accelerate these electrons with a few 100,000 volts. And that means this electron quantum mechanic particle is in the order of 50 to 80% of the speed of light. So fully relativistic at that point. And it hits a sample, so it hits our atoms, our crystals, and lots of things are going on. And these are actually the signals that we are working with. Electron microscopy has the advantage that there are a lot of signals. The electrons hit. The electrons interact with the atoms very, very strongly, and electron microscopy has a disadvantage. The electrons interact with the matter very, very strongly. The problem is there is so much information there that you're trying to throw away as much information as you can to get to the properties that you're interested in. So if we have this electron, hits the sample. If the sample is very good, 99% of your electrons will just go through the sample without seeing it. So it's electron transparent. A few percent are scattering out. So that is what we know from X-ray diffraction, neutron diffraction, except that we are diffracting much more. the electrons interact with the atoms also inelastically. That means we transfer energy to the atom. This energy loss, so this transferred energy, we can see in electron energy loss spectroscopy, which we do on Wednesday. These excited atoms have to fall back into the ground state, and that gives rise to Auger electrons and the X-ray photons. The backscatter electrons are actually just scattered electrons coming back. So just scattering in all directions. So diffraction and imaging, we do both in the electron microscope, and we can switch backwards and forwards as we want. And so here are the different with and without energy transfer. So I have now elastic scattering and inelastic scattering. I define these terms, right? So if we look what kind of modes we have, a few of them are listed in this table here. Electron diffraction and imaging are the two different ones, and you can have different kinds of imaging and different kinds of diffraction techniques. It depends on where you focus. It depends on whether you have the beam parallel or convergent, and in both cases you can do either imaging or diffraction. And how do we do that? An electron microscope, very, okay. I have a lot of stuff in my way. I hope you don't have that. Okay, here we are. This is our old microscope, put on the sides, and normally they stay upright. We start on the source here. So that's where we get the electrons out of matter and accelerate them. We have a gun part, so that is just forming the probe. Our electron optics starts about here. That is a gun aperture. And then we have a condenser system that does the illumination. So we have two different modes, roughly, a parallel one and a convergent one, as I said. And so usually there is some amount on a microscope where you switch backwards and forwards. In our case, it is TEM or STEM. In the old one, it was TEM and spot, so convergent or parallel. And you have different options how wide these beams are and how much they are converged. So we have different options here. They are, if you wonder whether you have to do that always, if you're not a microscopist, they are just stored values that an engineer aligns it with, and you just click the buttons. So that's what we're going to do. You can switch the objective lens on or off if you have an objective lens, which is right at the sample. You get higher spatial resolution, but you can switch it off, and then you get a larger field of view. If we go over, we have after the sample and this objective lens, we have a projector lens system. So that switches backwards and forwards between imaging and diffraction. We'll go into that in a moment. So we can switch backwards and forwards between image and diffraction just by clicking this button, and the first lens will change its strength. And also magnification or camera length, which is magnification in diffraction mode, is all done in this projector lens system. And it's just a whole bunch of other stuff. We also have an energy filter that sits either in the column or it sits below it. The main thing is we bend the electron beam. And if you bend something with a magnetic field, the faster electrons will not bend as much as the slow ones. And so you have them sorted by energy. If we look up here, image and diffraction, we have them sorted by location or by the angle they scatter. So we have three different modes that we now can combine backwards and forwards. And that are all the different techniques that we had up here. So here are all the different combinations of what you can do. And as I said, so you, generally speaking, you have a lot of different settings to make your life easier. So we have this relativistic quantum mechanic particles, and everybody with physics background will say, oh no, field theory. Feynman. Thank goodness we don't have to do that. We can actually go back to the geometric ray diagrams. And here, no. Okay, here we are. This is my ray diagram. How does that happen? Let's zoom in here a little bit. Okay, so that's why I was using this widget matplotlib part. So if we have a point on the object, everything that goes through the exact center of the lens will stay on that center. Everything that goes straight towards the lens will be hitting the sample in the back focal plane in the center. And any other angle, let's go back, will have them sorted by angle at the back focal plane, and in the image plane, the spatial point will be magnified or demagnified in the image plane. And these two rays here will actually define unambiguously where this image plane is, and that means we need only to define the back focal plane. And the back focal plane in an electron microscope, unlike other microscope, can be modified, right? So I can make it, the lens, the strength of the lenses can be changed, and I do that by changing the magnetic field of these lenses now in all cases right now in electron microscopes. And so I have a coil, and the current through that coil will change the magnetic field, and that will change my back focal plane. The magnification of such a lens is defined by the distance of the object plane to the lens and the distance of the image plane. And that is directly related to the back focal plane, as we just saw. And so again, I can, okay, it's probably too long. Let's go to something smaller. And so my demagnification here, right? One is 1:1, and I can go backwards and forward. So the magnification is directly determined by this V over U, just the distances. So I change magnification by changing this magnetic field. And so what do we change? As we saw before, what we change is the condenser lens settings to change the illumination of the sample, and we change the magnification in the projector lens settings. The objective lens we keep as stable as possible, okay? Objective lens, I don't know, does anybody know how much an objective lens in an electron microscope does magnify? Anybody in here? I'm sure as we had a chat here. No? Not bad. It's about 30. So 100 times is pretty good estimate. And so, but if you have 6 lenses that do it with times 10 afterwards, so each of these lenses don't have to be as powerful as the first one, you get a few million times very fast, right? Okay, so everybody understands now we just changed the currents. And we have to have another definition that is focus. In our case, defocus. We have overfocus and underfocus. And if we defines it with a convergent beam, it's easiest to understand that, right? So overfocus is above the sample and underfocus is below. It will become important in a moment. And to be clear, we always converge the sample in one way or the other. 100% is not possible, but you know, if you're talking about microradians, we usually call that parallel. Okay, I posted it just a few seconds ago. Can you repost them? Okay, so you get it reposted, no problem. The convergent angle can be measured in diffraction. In a parallel beam, all the diffraction spots are point, right? So it's the angle that you diffract into. As soon as you open up the convergent angle, these spots become this. And we use that in convergent beam electron diffraction, and we use that in STEM. Maybe look at that, you'll see it directly. So the lenses provides illumination and the magnification. We can switch the modes backwards and forwards. It allows to discriminate the angles, and apertures actually restrict information that's going through. And so we are going to set these apertures, and the direct and complete understanding of that is something that's a lifelong excursion, actually. So I'm still on that travel. Resolution is defined by the Rayleigh criterion. It is actually best defined as thinking in angular resolution. So magnification doesn't have really any physical meaning. The only problem is resolution. And angle resolution is what we have to think about. In optics, with the best optics on the clearest day, whatever, from Earth, you can see about that there is a window on the space station. So that's what the optics can do. So that's, you know, very small angle. With an electron microscope, your resolution is a little bit better. If you are thinking of having a penny on the moon, with the electron microscope, with that angular resolution, you can actually read the mint date. So there is a significant resolution increase by using an electron microscope that comes from the very, very small wavelengths. So this angular resolution tells us two things. We can read the mint date, or could read the mint date with an electron microscope. The problem is finding the penny, and that is usually the problem in an electron microscope, finding the right area. Okay. As we said, it's given by Rayleigh. We have this equation here. It's based on the first Bessel function of the first kind. And it's depending on the wave number or wavelengths on the aperture. And then we get an angle of observation. And that did not work. I have some problems with that. That's wrong. Okay. So my new version of Jupyter Notebooks don't have that. So if we go to our Google Colab, and I restarted apparently. No, we are probably not longer on here. Has to be restarted. Okay, it's not very good. We waited too long. I thought I had two options here. Let's see whether I have a third one. I just have my I hope this is still running. If you are online and following that, and you probably have that already. See that? Oh, okay, here is the resolutions that we are thinking about. Let's get rid of this one here. So, okay. So the new Jupyter Notebook apparently has a problem. I discovered it this morning. It was working well before. Of course, I updated it, and that was a mistake. So, the Rayleigh criterion gives you the smallest distance two objects can be separated in, and unambiguously tells there are two objects there. So that would be here the center part. Obviously, this part, these features overlap, but you can tell there are two. So that is the Rayleigh criterion. If they're closer apart, it's getting easier and easier to determine them. So what we call point resolution is if you can unambiguously tell the two features apart. The information limit is, I have, of course, some information about my resolution, and this particle here is in the horizontal direction about twice as wide as it should be. So I know there must be two objects in there, and I can fit these two objects into this peak, in this broad peak, and determine the information in my image. So there is a difference between point resolution, directly observable, and information limit, where you need some amount of additional information about your instrument. Let's go back to my So the point resolution can then be calculated. I hope the rest is going okay. And so with, depending on our features, we have a resolution of a certain amount in milliradians. In principle, we should have picometer resolution if you put that into the Rayleigh criterion, because we have picometer wavelengths and we don't reach that. So we reach about, on our microscope at 300 kV, we reach 42 picometer. Somebody else. Okay. There was a question possibly, I don't know. Put it in the chat, please. Okay, so the problem is that our lenses in the microscope are really, really, really bad. And so we have lots of aberrations. And the question is, how do we visualize that? I do that in the example of, okay, about that much, of the so-called spherical aberration. And so first we have to think about an ideal lens. In an ideal lens, all electrons or all rays that come in parallel will be focused on the center, on a single point in the back focal plane. And also rays that come out of the lens will be perpendicular, since it is hitting in a single point. They have to be perpendicular to a sphere. So it's three-dimensional, right? So I have only a two-dimensional material. That's not what our microscope does. The magnetic field in a magnetic lens is actually not what's focusing our electrons. It is the magnetic field gradient, because if you have a lens, electrons can do, right? So physics knows it should not be doing anything, because the direction and of the magnetic field and the electrons are the same, but outside there's flux line difference. They're tighter on the rims and they're in the center. And so the magnetic lens will focus the outer line rays more than the inner line of the one closer to the center. That's exactly opposite in an optical microscope. But in an optical microscope, we have convergent and divergent lenses, and so we go over the same amount through the material, so the path length distance is over the same. Or on our icons, they change the magnetic, the dielectric constants. So in our microscopes, we can't do that. We have this change in the back focal plane. And because it is like that, so basically instead of a sphere, we have now an egg, an ellipsoid. I call it an egg. It's much easier to see. And the aberration function now is the difference between an ideal one, ideal lens behavior, and the lens behavior of the real one. And that is the screen plot. And we go into spherical coordinates, and so we basically thinned it out, and we have the screen part here that shows us how the path differences are between the ideal one and this red one for the aberrated. This egg, what is ellipsoid, it's an ellipsoid for the Gerd aberration, but you can imagine it's much closer to an egg. Actually, it's much closer to an egg that has been dropped a few times. So it is really all kinds of shapes. So this aberration function is really quite mangy. So that's what we have to take into consideration. If we go back to this aberrated, okay, let's get rid of these ones. So the disk of least confusion is then over here. That means you have to go a little bit in under focus. So we move this part in here. So we go a little bit in under focus to have the disk of least confusion in our back focal plane. All microscopes are operated in under focus for exactly that reason, okay? So we always want to be a little bit in under focus. The aberrations can be classified. So we have a very complicated function. We don't know what to do with it. We make a Fourier expansion. And in the Fourier series, the Fourier coefficients are named. The zero order ones are just a shift, left, right, up, down. We have defocus. Defocus is just a change. So it's in a three-dimensional plot, it's only one value, right? So we stay on the optic axis. We have astigmatism. That is the first order, and it has a twofold symmetry. The other one has a rotational symmetry. Then we go to the second order, that is coma. And after that, the nomenclature of this aberration coefficients get a little bit hazy. We have this threefold astigmatism. If you have a beam, and we will see that hopefully with having some amount of aberrations in the microscope, that is when the electron beam, when you focus it down, is triangular. So it's really just a triangular kind of beam. Then we have spherical aberrations. That's what we just were talking about. And we can go up to fifth, sixth, seventh generation there. Where are we in time? Okay, good. So this is our aberration function. It depends on the angle, obviously. So we want it to be in polar coordinates on the distance. So we have our polar angles, and that is our aberration function. According to Krivonek, so he made it so that we can, in his formulation of that, we have two different terms here. We have the aberration coefficients back here, and we have an order term in the beginning. And the order is always m+1. So like in Python, apparently everything starts at 0. So, and we have a cosine and a sine. So it's an exponential function back here, as we are not surprised with the Fourier efficiency. So we have two more relevant terms. One is the acceleration voltage, and we have a chromatic aberration. So our electrons that we have are effectively don't have all the same speed, so it's not monochromated. They have a variation in their speed, in their energy, and Z is actually an additional defocus, right? So if you have a slower electron, it will be deflected more, so it will have, so a slower electron would hit here, right? And the faster ones over here, so they have two different crossovers in the back, also behind the lens, and again, that is a defocus value, basically, so that we cannot discriminate. So how do we measure the aberrations? We have to correct them. So that was the big innovation of the in around 2000, was more or less independently done by two companies, Neon by Krivanek, Andrei Krivanek. He had guest professorship in Oxford, and he was doing it then. And then the other one was CIOS, Max Heider, Harald Rose. They started their company, and so they had two aberration correctors. And before that, we were just limited by however good our lenses were. And now we can correct them. And that was really the biggest revolution, and mostly because why we are here, I guess. And there are also two different methods how you can do that. One is a Zemlin tableau. You find the link here. And the other one, Andy Lupini. So he did Oxford. He was in Cavendish lab in Cambridge, of course. Sorry, Andy. Did you hear that? Oh, Andre. Okay, so that was done in the Cavendish, and so in his PhD thesis, he figured out how to get the aberrations out of the so-called Ronchigram. In the Zemlin tableau, the basis for that, I went through that quite quickly here, more quickly than I anticipated. So in the Zemlin tableau, what you do is you take your beam and you tilt it. Now, if you tilt the beam and your beam is perfect, it's always round, right? Maybe a little bit an egg shape as you would expect that from. But if it is aberrated with higher aberrations, then you have quite distinct patterns. If it is defocused, it stays defocused. That's the first part. So you tilt it, we have a beam that is an ellipse instead of round, right? And then you tilt it, it always stays. So this is A1, this is our astigmatism. B2 is coma. Coma is when you have a lens and you're going through the center, but you're not going parallel with the optic axis of the lens. And so what happens is that perfectly round it moves down here. Okay, here we go. Good. So in the coma case, you tilt your sample. Once you get a little bit closer to the optic axis and left, and so you have significant changes of your figure, and that is on that case. A2 very similar. So we have a threefold astigmatism. It's not longer easily explained with this simple tilt picture, but you can see it has very distinctive changes in the shape. C3. Okay, the astigmatism is always the same if you tilt, right? So we have a round beam, we tilt it over, we cut it, so it is looking like an astigmatism, but it depends on in which direction you do that, and any kind of non-roundness is due to the astigmatism. Like feature, and then we have S3, so a higher order one. It's a third order with threefold, twofold. Okay, we can go back. Now I'm getting confused as well. I have them translated here at some point. C3-2, so it's a third order one with twofold symmetry. And then you can see the A3 is the third order with the fourfold symmetry. And the symmetry is what we are after in the tableau. Clearly, S3 is twofold. I should have remembered that. Okay. And the A3 is a fourfold symmetry. And you can see that in the tableau figures. So we are looking at symmetries, and so this is a very, very fast, was a very fast journey to go through that. Let's see how we do that. Oh, there's a lot of things. Okay. I cannot, I only have my mouse, I'm sorry. Okay. So why does astigmatism arise? We have said over here. So you have a lens and astigmatism, okay, here. The lens is not perfectly rotational symmetric, so it is, in our picture here, if that is the black one is the XY direction, or X. Okay, so let's assume this one is X. So if this one is in the C direction, we focus here, and then the strength in the other direction is stronger. So depending on where the beam hits this lens, right? So either in the horizontal plane or in the vertical plane, you have two different focal lengths, which will over here in the image that you are projecting will make it like an ellipse. Hope I explained that correctly, not clearly. It's correct, but it might not be clear, but you have to go back to a three-dimensional picture in your mind, going away from this. So we rotate this picture here from the black one by 90 degrees around the x-axis, and then we have the blue one, and that is the astigmatism. That's the simplest of the aberrations, right? the easiest to understand and picture is spherical aberrations. It's a higher order. And with coma, you can also see that if these beams don't go through here along the optic axis, then they would be somewhere on the side. And that is in 3 dimensions. So each direction, each angle that we rotate will be different. And you want to have some rotational symmetrics. That's the first thing. The secondly is you want to have all the rays as closely as possible hitting in a single spot. In STEM mode, this small spot will be our probe that we are moving over the sample, and that will be discussed in the 3rd lecture. The second one, we will go into how to correct these aberrations. And we will do this Zemlin tableau. Before we go, make a short break here. Any other questions? Okay. What do you need? Okay, that is actually a good question. What do you need to tilt? All you need is a deflector. So the electron microscope. I didn't understand that. I think I just mute that person. Put it in the chat, please. To cover till now. Okay, not tilt. I was reading that wrongly. So we have this lecture recorded. You can go back once it is posted to check it out. And the other thing is, if you want to catch up, it is on, for the ones joining late, it is on, no? Where are we here? It is in under Gerd Duscher on GitHub, and there is an ML stem. Okay, let's go back here. Repositories. First one, if you go to that one, summer school, and then day 1, 9 a.m. So the next ones will be aberration correction, and then Ronchigrams. Then we have actually covered most of the STEM parts. I wanted to just log on here for a short on the microscope. If you're on the microscope, the first thing you want to do is you want to open the column valve. Yes, the recorded session will be shared, of course. Otherwise, it will, and if you're registered, then you'll get the link to that. Yeah, and then from IoT, I hope I pronounced it correctly in the, yeah. Okay, so the rays are differently depending on where they hit the lens. They are not ideal. That's exactly right. Okay, Okay, so textbook, we have a few textbooks that we have put on our web page. cool program. And we have resources. The main one is Carter and Williams. So that's lots of pictures. Cool and Reimer. Reimer is very, very dense. If you want to look something up, that's where it is. Every word counts. For electron diffraction, I learned most of my electron diffraction from Spence and Zhu. Calculations, Kirkland and Eels will be later. There's also Jupyter notebooks that are in PyTem Lab and in my lecture that I do for the University of Tennessee. Okay. So, yeah.
I'll use the mic. So if some of the aberrations come about because none of the lenses are perfect, how can you correct them with other lenses? Because those lenses aren't perfect. So you just keep adding a bunch of imperfect lenses and you get more aberrations, or what do you do?
So the idea is to have the objective lens doing most of the magnification. So that is the one then that determines everything. All the other ones do less magnification and are not quite as relevant. And so what you're trying to do is you correct for Z aberrations. In the case of the stem, you have your aberration corrected before the objective lens. So you are changing for each ray on hitting the lens so that after they go through the lens, it's as close as possible to the back focal plane together. So it is basically a bad lens that is well designed to compensate the real bad lens. If we make a little bit of a break, I can bring the third aberration corrector and have it go around. Okay. So, okay. Are we in time? Few minutes here. So let's see. I wanted to share that. So we open our lens. Where is the convergence angle? What do we see? What was it? So this is the diffraction pattern. And what is the convergence angle that we see here? Obviously, yeah? Yeah, it's what we see. The bright thing, right? The bright disk is our convergence angle. Actually, it's defined from the center out, but instead of having a spot, right, it's a disk. And it's alive, at least it looks like it. Okay, oh, that was really good. It looks like it's alive, so we are seeing here the coherence of our source. Actually, it's the coherence of the whole system, I should say. And so looking at this picture will give you actually a very good idea about the status of your microscope. This is in the back focal plane. On the sample, obviously, it is small. If I just move over to where we have, I have too much stuff in my way here. So we move this probe over the sample, and this is a so-called C-contrast image. If we move that down a little, no, not this one. You see my mouse? Okay, it's a bit slow here. So over here, this green stuff, the top ones are the EDS detectors. So we will talk about energy dispersive X-ray spectroscopy on Wednesday. We have a beam, and we have the sample. We have our high-angle annular dark field detector. So in this case, wherever we have electrons scattered to very high angle, that is where we are seeing something on that detector. And of course, the heavier the atoms are, the more you have, the more scatter out to high angle. So it is naively to interpret this kind of image. So it's a gold sample on carbon. Wherever it's dark, that is where the carbon is. Wherever it's bright, that is where the gold is. Okay. We have a little bit of time here. We can zoom in to a decent magnification. And without focusing or anything else, we made a nice hole here. Let's move to a different spot. This might not be enough. Let's see whether it works. It's now at a random position. We zoom in again. The relevant thing is not the magnification. Okay, we have no focus here anymore. I have all this stuff in my way here. And we have to focus. So we change, in this case, the magnetic field of the lens. And we see our atomic resolution image. And that's without having aligned anything. So we are going to align it. It's a little bit aligned. So I played around this morning from home. And we can clearly see here, we have on the right-hand side a different pattern than on the left one. So we have a grain boundary. We are looking down in this crystal in different orientation. So the projected potential, so the projected location of the atoms are at different points. And so here they are clearly, let's do that a little bit slower. So with a slower scan, you see the different atoms here closer, and our resolution that we normally look in the Fourier transform. So we have sub-angstrom resolution right away, and that is what we want. So we want, but we don't only want good resolution. What we want is good resolution that we know exactly what it is, because we want to go from the point resolution to the information limit, right? So we want to get better than that. And this kind of projected potential can actually trick you. So if we had many different parts where the pattern looked different just because the probe was triangular, was overlapping at places. And so that is where you have to be careful, and that's why we want to have our microscope as well aligned as possible and with the parameters known so that we can handle that correctly. Okay, so I'll stop that here, and then we'll talk more about how we do aberration correction. As anyone knows, if you go away from the microscope, the first thing is you close the column valve so that if anything stupid happens, your gun is protected. Changing the gun is in the order of $1 million, and it takes, which we have a maintenance contract, so it's not really a financial disaster. The real disaster is you're out of a microscope for about a month, if you're lucky. So we want to protect it at all points in time. The source here is a Schottky emitter. That means the electron source is always on. All we do is open the column valve and have a beam immediately. So let's make a short break, and then we'll do some aberration correction here.